right. Is the recording on? Or?
Yep, recording has started. Okay.
Yep, I have to consent. All right, we are on.
Yep.
All right.
Do we want to make announcements first?
Yeah, I was going to do a couple of announcements. First question, how many folks are interested in doing a lightning round meeting? So this would basically be kind of us that, come to the meeting and or want to present. We would do 5 or 10 minutes for a small short session and just have a collection of those. I've got a topic that would be good, and I just wanted to see how many people, and you can just raise your hand or shout out or something. How many people would be interested in doing that? Just a collection of real short. So there's 3, 4, if I count myself. Okay, that's enough.
I didn't quite get. So there are many candidates, and we need to select some of them, or
No, so,
what's the purpose?
No, so what it would be is for folks who don't want to, who have something they want to talk about, for instance, but it's small. So it'd be like the lightning rounds at CPPCon is what I'm thinking. So what we would do is take one of our sessions and just basically have as many people as want, or as many people can fit, do a short 5 or 10 minute presentation, and that would just be the entire session. So it looks like we've got about 4 to 5 people, which would work just fine. So I will schedule that in somewhere. It'll probably be toward the end of the year. So get ready for that, and I'll start announcing it. And Brett, you had a note on CPP Now?
Yes. I did send out an email to the volunteers who did CPPCon, but if any of you are interested in in-depth knowledge of what will be happening in C++, there's an event called C++ Now, and that starts in May. It's on May 2nd through the 7th. It will be virtual, just like last year's CPPCon. So we will be using Remo and StreamYard for the running of the event. And we're looking for volunteers if anybody is interested. So you don't have to leave your house, but you will have to dedicate a couple weeks to the event because as we did at CPPCon, we had the first week, we had the volunteers hook up with the speakers and work with them. And then the next week, they did the actual session. CPPCon will be happening again. Whether it's virtual or not, it will definitely have a virtual component. So it's in October. So if anybody's interested, leave me a note. That's all I have.
Okay, thanks, Brett. And with that, we'll turn it over to Sonny, who is going to talk about C++ code safety using static analysis. All yours, Sonny.
Right. Thank you. Thank you, everyone, for joining me. I'm Sonny Chatterjee. I basically am an engineering manager in the Visual C++ team at Microsoft, and I enjoy working on static analysis. And recently, we have been looking a lot into how we can make C++ a more safe language to program in. And so since static analysis has been used in the past in Microsoft for detecting a wide variety of defects, we wanted to see if we could leverage its principles to add code safety in C++. And so that's what I'm going to talk about today. Let me just move on to my next slide. So in this talk, I'll cover why code safety matters and a little bit about static analysis. And we looked at some safe languages. As you all know, or many of you know, that Rust is a popular programming language for system programmers. It has its promises on safety. And in fact, it's one of the most loved languages in Stack Overflow for a few years. So we got curious and we wanted to see if there are any learnings from this language that we could bring home in C++ and adopt it. That way, when we start cooperating and picking the best from all languages, we provide the best tooling for our customers. So a lot of this talk, I'm going to talk about some of the learnings from Rust that we tried applying in C++, and what we found there. So then we'll talk about some actual real-world data from Microsoft production software. It's the Microsoft shipping software has lots of lines of millions of lines of C++ code. And one of the things the teams have to do is before they ship anything, they have to run these security and compliance tools. And some of these tools are, in fact, the rules from the static analysis that we have already implemented. And many of them are available in Visual Studio as well. Then I'll cover where we are today in terms of what we have in our static analysis tools and what we are building next. And in the end, I'll share some helpful links. So if you want to dig deeper into your topic or reach out to me or my team, you should be able to follow through the links and get back to us. And also, I would like to acknowledge contributors that have contributed to this area for the past few years. With that, I want to talk about why code safety matters. Well, basically, C++, it's a very flexible language with its promise of performance that we have used for decades. Last few years, I have been interacting a lot with the Microsoft Security Research Center, or MSRC, and we have been seeing different kinds of, when we find a MSRC class issue of security vulnerability, we try and find out if it was possible for static analysis to detect it. And in those conversations, it became evident that customers and security researchers, they have been asking for strong safety guarantees in the language. In fact, a couple of years back, there was a blog from MSRC that talked about some of the safety guarantees that safe language like Rust provides and how it can help system programmers. So also, it's not about performance and safety. We believe that correctness is equally important. People have higher expectations than ever from compilers. So the idea is if you can compile your code and then execute those binaries, then they would behave correctly as you would expect them to be. So it's not just performance and safety, but also correctness. And I'll cover a little bit of each in today's talk. It's not us, like I told, there are others thinking about how to write safe and reliable software. And the challenge for us was to see if we could leverage the power of static analysis tools that have been very successful for us in the past to, for example, write rules that prevent buffer overruns or write rules that prevent concurrency issues. And in the last few years, we have also used these rules to implement rules from C++ core guidelines that help people write modern C++ as they are starting off. So we wanted to see if we can use the same platform to write rules that make C++ a safe language. So in a nutshell, for those of you who haven't had a chance to use a lot of static analysis tools, it's basically it reads in C++ code and applies some clever techniques that look for certain defect patterns and reports these at compile time. So you don't have to execute your code or any test cases for these defects to show up. So the idea is, as you're developing in your favorite editor, these rules would run in the background and find defects for you so that you can fix them right when you are coding, essentially. So our focus today is on static analysis. And static analysis it considers each function in isolation and cannot see across function boundaries. And that distinction is important because there is the other extreme where we call there are tools for global static analysis which can analyze across function boundaries, but because they have to look at every function and there are different techniques, but they have to essentially build properties of functions so they can look across the boundaries. It kind of is expensive and it's difficult for us to provide these diagnostics when you're writing the code or when you're submitting a PR in real time. So there are different strategies in which local static analysis can scale. So you could rely on C++ types, or if you're using certain special types from the guideline support library, or if you're using some attributes, these local static analysis tools can understand them across the function boundaries and make inferences. So even without the full power of a global static analysis tool, you can be pretty effective. So what I'll show today, they are all built on the local static analysis engine that we have. Why is this important? Because it really is an effective way to drive quality upstream. It can help you find and fix defects at the earliest point when you're developing your code, and that's when it's cheapest to fix, as opposed to get bug, getting checked in and then showing up in the field and then having to patch that is kind of expensive. So all large corporations actually invest in static analysis in some form or the other. It also has been a very effective tool for us in enforcing C++ core guidelines, like I mentioned before. And it has already found a lot of safety and reliability issues for us, ranging from uninitialized memory to concurrency errors. So this was like a good experiment to try to see if we can use the same engine to implement some of the safety rules from Rust. So when we looked at Rust, I had an intern work for us last winter, and we asked him to just basically look at Rust and see if any of those rules from Rust make sense in C++. And the idea was not to like have a 1:1 mapping between every Rust safety feature and bring them over to C++. Some features are too restrictive, and it would kill the flexibility of the language. And that's not what we wanted to do. We just wanted to learn if there are any things in Rust that we could bring over to C++ without giving up on its flexibility and performance. So the other thing that we learned is, in Rust, safety features are built into the language. So if you break any of these features, your resultant code will not compile. No matter where you build this diagnostics in C++, you can turn off some of the safety features, and the compiler will still accept your code. So that there is a distinction there in terms of like the strictness in the compiler or the analysis tools between the two languages. So our challenge was to bridge this safety gap and see if we can identify any differences that we could bring over to C++. And we had to we wanted these to be statically checkable. And we wanted to see if we can use the same engine that we have used in the past to successfully build existing static analysis rules. And again, we did not want to create new attributes, or in Microsoft, we have these annotations that help static analysis tools reason about code, but we did not want to build anything based on custom attributes or annotations, but we wanted to rely on the existing type system in C++. Maybe we would understand a few language extensions in the guideline support library, and some core guideline rules. So we didn't want to impose any restrictions through custom attributes when we wanted to do this. So the exercise we did was to go over some of the big buckets of safety and correctness that we read about in Rust, and see if we could find any corresponding rules in the either C++ standard, so the compiler would implement them, or core guidelines so that we could implement them during analysis. And we tried implementing some of these checks using static analysis. So here are a few big buckets that we looked at. We looked at casting, which is an essential tool that's used by almost all C++ programmers, but incorrect casting can lead to type safety errors. So that's definitely an interesting area we looked at. We also looked at some statements that are error prone. We found like lots of logical errors when people use switch statements. So those are correctness issues. So we looked at them. We looked at smarter loops. If you're not using loops the correct way, you can actually end up accessing out of bounds. And so even though loops are kind of innocent on the surface, they can cause ugly bugs. So we looked at ways we could write safer loops. And also, when you copy, C++ is copy by default, and there are performance implications in the code you write. So we wanted to also be smart about when we use copying and guide developers to use copying only when it was necessary. And then we also looked at lifetimes, where you end up with dangling pointer pointing to some memory that's no longer valid, or you're trying to delete something that has already been freed, or you're trying to access something that has already been freed. So lifetimes is another big pain point for C++ programmers. And so we wanted to look at lifetimes as well, and also mutability in I can go over that in late. I'll go over that later in the talk. But I think there are some restrictions in Rust in kind of if you can't have like a mutable and an immutable reference to the same object in the same scope. Obviously, C++ allows that, but we looked at if we can have some sort of analysis to guide developers to do the right things when working with mutable and immutable references to an object. So first, a little bit about casting. So these are some things we just observed when we looked at Rust. It does not allow implicit casting among primitive types. So if you have here you have an integer and you're trying to convert that to an unsigned, and the compiler will not allow that. So that's an error that you will have in Rust. Similarly, if you're trying to convert a 32-bit float, which is a floating point to an integer, you will not be able to compile that code by default in Rust. C-style casting is allowed for some types using the as keyword. So in Rust, you can still use C-style casting. You're trying to attempt a conversion from a 32-bit integer to an 8-bit integer. And you can still see that this is bad because the value may not fit into that 8-bit. However, no conversion is allowed from an integer to bool. And for us, this has been like, we could relate a lot to some, as we were reading some of this, because at least in Microsoft, we saw there are a whole bunch of errors we found because of incorrect conversions from bools to H results, because a Boolean would be a true and a false value, and both of them are success conditions for H results. So if you mix that up when you're calling different APIs, they can cause pretty bad bugs. So here's an example in Rust where you're trying to convert an integer into a bool, and the compiler complains. Similarly, if you have an if condition that's an integer, it's an error in Rust because the if condition has to be a Boolean expression. Safe casting can be achieved using some concept of a trait in Rust. So here you're actually trying to do that safe casting using the traits where if the value fits in, it's okay. If the value does not fit in, you're using a default value of 42. Similarly, you can have an equivalent of optional in Rust using the try from traits where if the value has a conversion, then it says it's success, otherwise it's failed. So C++ has a bunch of rules around casting in the guidelines that if you follow that, you won't be making these mistakes with the flexibility of the language. So the guidelines help you use casts in the right way. So we looked at C++ core guidelines and we went through a bunch of rules there, like don't use reinterpret cast, don't use static downcasts. In fact, we created a type in the guideline support library. It's an extension type extension called narrow and narrowcast, which actually checks for data loss when you're downcasting. Const casts are bad, so don't use that. Don't use C-style cast. So there are a whole bunch of rules here, and we have a profile in our static analysis rule set in Visual Studio that basically implements this as C++ type safety rules. If you have that profile on in your project, then it will guide you to not make some of these use some of these casts in your program. So that way you have a lesser chance of making a type safety error. For switch statements, what we have seen is Rust has a pattern matching construct that covers similar functionality to the C++ switch, but it's a lot more flexible than that. What's interesting to note here is you have to cover every case. So when you're looking for this switch statement on an integer, you have 1 and 2 that we check for explicitly. The underscore is like equivalent of a default in C++. If you take that line away, your code will not compile. So the compiler kind of forces you to inspect every possible value when you're doing a match construct. Similarly, if you have an enumeration that has 3 values, all 3 values have to be checked. Otherwise, your code will not compile. In C++, there are no restrictions in the language as such, but we have seen that these can be cases of correctness issues in code. However, there are core guidelines that do lead you to do the right thing. So there are rules that say switch statements over a non-enumeration type should have a default, and switch statements over an enumeration type should either have a default or cover all cases. and there shouldn't be an implicit fall through. You should have to make that explicit. Rust, on the other hand, does not have any fall through construct in its matches. So I'm going to quickly show a demo of what it looks like when you're using this in the program. So this is let me know if the screen is not readable. I can make it a little bit larger. Otherwise, I'll just go ahead with the demo here. Is that readable to all of you?
It looks good.
All right, thank you. So here is a function foo. It takes an integer and it has a switch statement on that integer parameter. And it has two cases, case 0 and case 1. We are breaking, everything looks good, but we have a green squiggle in your editor that says, hey, the switch statement does not cover all cases, and consider adding a default label. This is a really bad example because this is not doing something fun, but there are subtle cases where you would find that if you don't add the default, you will run into correctness issues. So if you add the default here and decide to explicitly break, that makes your intent clear to the static analysis tools. And then if you save your file, the green squiggle should disappear. The second example is a little more subtle. You have a switch statement on an integral value. And here in case 0, you're doing something and you're explicitly falling through by using the fall through attribute. In case 1, you have a conditional check. If the condition is true, you call a function. Otherwise, you fall through. So when you call this function, if the condition is true, you are in fact falling through, but you have not made your intent clear. So it could be a logical correctness issue where you would expect this to have a break, or it could be a fall through. So the tool does not know. So if you really meant to be a fall through, you would have to add that here. And otherwise, you have to put in a break. And you have an error here saying there is an unannotated fall through between switch levels. And if you really didn't mean that, you would just add a break. And your warning should disappear. Next, we looked at the way Rust uses its loops. It does not have any C-style for loops. We know that C-style for loops, they are kind of error-prone and complicated. You have seen lots of bugs when we are using containers because we change the containers while we are iterating over it. I've also seen bugs where we do wrong calculations on the loop index and then end up accessing containers out of bounds. So these sorts of errors can be prevented if you have a range check iterator pattern in the loops. And that's the only kind of loops that you get in Rust, right? So it forces the loop variables to also be scoped to the loop itself. So here is an example where, a very simple example where you have an array of 5 elements and you're iterating over its elements, and you cannot access those elements past its bounds in the way the loop is defined in the language. You can also do fancy operations on the loop. In this case, you're actually reverse sorting the collection and then stepping down by 2 and printing them. C++ does have, the language allows you to have the C-style loops, of course, but it also has rules where it can guide you to not make some of the common mistakes when using loops. So it enforces, like it encourages you to use loop index variables inside declare them inside the body of the loop. In this particular example, there is no reason why I should be declared outside. It can be scoped down unless there is like a programming need for this to be outside. Similarly, in this function, in this if block, X is computed outside its scope, but it can move into the if statement. That way, it does not have to leak outside. We also flag reuse of loop index variables. So in this example, you'll find that the loop index variable I is used within the 2 loops, and they are actually set and reset and set in the second loop, right? So the variable is not read in between. So there is no reason why we should be reusing that variable into loops and exposing that outside the scope of the loops. So there's also a rule that encourages you to convert your C-style for loops into range for loops. So, and that way you can eliminate a whole class of errors where you can accidentally end up accessing a piece of memory out of bounds. So this is a typical C-style loop where you are actually accessing each element of a vector from 0 to vector size. And I've seen more predictable patterns where people use these iterators. But even with iterators, you can end up accessing the memory out of bounds. This is what we would recommend you do in C++, where this is like a pretty tight loop. The loop variable is scoped within the body of the loop, and it also is a range check for free. That's something you get for free from the compiler, and you wouldn't be accessing this vector out of bounds. So here we wanted to have a warning there, guiding the developers to not use C-style for loop and encourage them to use for range instead. And I wanted to go a little bit into how static analysis does its analysis when it sees patterns like this and comes up with these recommendations. So in this case, it sees that there is one loop index variable I, and there is a condition that's bound by the size of this container. And there is a very simple side effect free, like simple expression plus I, that's like typical incremental operation. And in the body of the loop, I is only used for indexing and nothing else. So there is no pointer arithmetic happening. There is no access like I plus 1 or I minus 1. There are no assignments to the loop index variable. There is no such thing happening. And also the vector is not mutated within the body of the loop. So there are no side effects on the container. Example of a side effect would be if you had a pushback that changed the size. So when all of these conditions have been observed, then the static analysis tools can, with a fairly high fidelity, warn and say, hey, this is a loop that you can easily convert to a C-style for loop, and that makes your code a little bit better. We looked at smarter copying next. So one of the things that we learned from Rust is it's a move by default language. So copying semantics must be explicit. And obviously, we had no intentions of imposing any such restrictions on C++ because C++ is a copy by default language, and our intent was to not change that at all. However, the move by default semantics in Rust is actually a pretty big part of how it does its memory management. It manages lifetimes, ownership, and borrowing. It also allows Rust to prevent memory leaks and dangling references and provide some sort of compile safety in many different contexts. So we wanted to see if we can bring some of these safety guarantees in C++ without changing its copy by default nature. So just to give you an example of how a move by default language looks like or feels like for those of you that haven't used this construct, you have a big structure that's assigned to the variable A. And when you have a statement like you're assigning A to B, A can no longer be used because it has been moved from. And so that's a compiler error. If you need to use A, you have to actually copy that, use the copying semantics explicitly by cloning it. In C++, there are rules that can avoid you making unnecessary copying or expensive copying. So, for example, this is a very common pattern we have seen in a lot of production code where people don't necessarily realize that they are copying objects when they are looping over, and that definitely contributes to a lot of unnecessary copies and performance. The performance is not as good as it could be. So here is an example where you have a vector of a complex type, and you're iterating over that vector where each element is a complex type. Copy occurs in each iteration of the loop, but the X variable is never mutated within the loop body. So this should now become const ref. That way we are not copying each element of the vector, and we can prevent that cost. So for static analysis, again, the way we identify these patterns is we use heuristics to identify expensive copy, and then we suggest using a reference here. And by expensive, the way we defined our heuristics here is any object that's being copied is like if it is more than 2x the platform dependent pointer size, or if it's not a view, because views, like, they are not supposed to own any memory. They just are views into memory, and they don't contain any memory by themselves. So views are perfectly fine to be used by as a copy. And if they're not smart pointers, then if the loop variable is also not mutated inside the loop body, then we can actually, with a fairly reasonable confidence, say that hey, you're doing an unnecessary copy here, and you should be able to avoid that. So here is an example of a unnecessary copy that's happening. You have a large structure which has a vector of which is like an array of integers, and you have a small structure which is just one integer. And you have two functions, one that takes that its parameter by value. So there is a there is and there is another function that takes it by reference, and there is a mutation happening in the second function. So you have a function foo here that takes a const ref to the large struct and a const ref to a small struct, which are both vectors of that large struct and small struct respectively. And here in the first loop, you find that you're actually iterating over that large collection and then passing it to this function takeInt. And so we know that this element is not mutated inside by takeInt because it takes it by value. So we can totally avoid the unnecessary copy here. And we have a green squiggle that tells you, hey, there is a potentially expensive copy happening here. Consider making it a range for loop. So making it a const ref. So if you add this line, the green squiggle should disappear. The second example is where we have a same pattern for the small, the vector containing small struct. And we are typically okay with that because the size is not greater than 2x the platform size. This third example is where we are iterating over the large vector, but we are actually mutating its elements. So obviously, in this case, we cannot suggest a copy is necessary because it's being modified. Similarly, if you find that in the last example, you will find that we are passing it to a function that takes it by reference. So we assume that the data will be modified. So we don't suggest you changing this. So we allow that copy to happen in this particular case. So the second rule we looked at is suggesting to use const auto ref instead of auto when assigning from a reference. So this is another interesting difference we found in Rust, where if you assign the return value of a function that returns a reference to a variable, the type of that variable is a reference. So auto implies a reference type in Rust. There is no copy that happens. In C++, though, when you assign a to the return value of a function that returns a reference, the type of a is not a reference. There is a copy happening here. It's a little bit different for a pointer because the type of b is still a pointer. For anybody who is new to C++, it can be a little bit confusing, different than pointers. So it's inconsistent, and it's an expensive mistake to make, right? If you forget to put that reference where you could on the auto. So there is a check that we had for this scenario where you have a large struct, which is again an array of integers, and then you have some struct which has a data member of that large struct, and it has a method called getLargeStruct, which returns the const ref to that large struct that it contains. In foo, you have a const ref to that sum struct, and in the first statement here, you see that what we are doing is we are calling that method getLargeStruct, which returns a const ref to it, and then it gets copied to the large struct. So in this function, we are not using that large struct, we are not mutating or changing it at all. So we realize that this is a case where we can be more efficient by suggesting to mark this as a const auto ref. And if you add that, then the green squiggle should disappear. In the second example, we do get like a const ref and the copy happens here, but that copy is necessary because you're actually writing to that in the next line. So we don't ask you to change it in this particular example. The last one is also interesting because you have some struct which returns a temporary object, and then you ask for getLargeStruct, which is contained within it. So you get a const reference here. If you don't allow a copy to happen here, and the very next line, this would disappear because it's a temporary object that would get destroyed. So a copy is necessary because the lifetime is not extended past the statement. So we realize that this is a good use, and we don't want on this particular usage. Next, we looked at lifetimes. So Rust's memory model makes it difficult to leak memory. In C++, we in fact have a lifetimes profile that's available in Visual Studio. And the idea there is to statically check against any memory that has been invalidated. For example, here is an example where you're basically putting in the address of a local in a vector. And obviously, the local will that piece of memory will disappear once this function returns. So you'll end up with an address that points to invalid memory. And we want C++ tools to be smart enough where if it spots this kind of programming errors, we can guide developers to do not make these mistakes. Our intention is not to add restrictions in existing memory model that we have, but to make it easy for people to write code and not make mistakes. I have a demo for the lifetimes profile here that we built for this example. So for lifetimes, you can see you have a vector of 3 elements. We basically have an iterator pointing to the beginning, and then we write to it a value of 0, which is perfectly fine because the iterator is valid here. In line 8, though, we are pushing back an element to the vector. And when you do a pushback, the memory layout can change. So this iterator is no longer guaranteed to point to a valid piece of memory. So in line 9, when we are trying to write to that iterator again, we issue an error saying this iterator has been invalidated. So we say, don't reference a pointer that may be invalid. And results on line 9 may have invalidated. On line 8 may have invalidated that iterator. So our expectation is you would have to do something like we begin again, if that is what you meant. And it should disappear. The last bucket we looked at is immutability. Rust is immutable by default. So for those of you that have not played around with Rust, these seem very odd to me, where you have a variable A, it has a value of 3, and you're trying to self-increment it by 2, and that's an error because you've not declared it as mutable. So everything in Rust is immutable by default, which is again different than C++. Again, our intention was not to change anything about C++ in this case, but to see if we can, if the benefits of this, if we can implement that in C++. Rust forbids having a mutable and immutable reference to the same object in the same scope. And this is an interesting example as well. You have a variable that has a value 3. You have a const ref, and then you have a mutable ref. Mute is the keyword that's used in Rust to mark a mutable reference. And you're incrementing this value to 4 through the mutable reference. And then you're passing that, sorry, to a const reference in this function. And you get an error from the Rust compiler that says, hey, you're borrowing an immutable version while it's mutated above. And that's invalid. If I move on to the next slide, in C++, you have const correct, a whole bunch of const correctness rules. In fact, using const is viewed as a good programming practice. There are several popular blogs that have come across on this. Core Guidelines also has rules that say you should be marking anything that's assigned only once as a const. And we have a profile in Visual Studio that enforces these rules in your project. However, this next example here, which is exactly the same example I showed you from Rust, is interesting because, again, you're incrementing this variable's value through the mutable reference, but then accessing it through the const reference. And today, you would get a value of 4, but it did bring up an interesting question and made us curious that is that something we should allow going forward? Like, is that really what the programmers mean in this case? Because this is definitely an error-prone pattern. So to summarize, this was all part of like it started as a winter internship, but I think it got us to a point where we could actually take this on as the bigger challenge for the team. And this has been like a pretty important theme for our team to kind of look at these in more details, and not just as Rust. Rust is just one example that we did in the internship, and that's what I shared today. But I think to look at how we can use static analysis to identify anything that makes C++ a little bit unsafe, and if we can have rules to bridge that gap. C++ core guidelines has rules covering many of the big ticket items, and we have many of those implemented in Visual Studio as well. For those of you that use other editors and tooling tool chains, I'm sure there are other checkers that cover these areas. And even though we have a lot of rules from different tool chains, there is a lot more work needed when we look into what is available today. There isn't a lot of rules that look into how you can make mistakes when you're using loops. There isn't like a lot of checks on lifetimes with that have less false positives and is enforceable, because for something to be enforceable, it has to be pretty accurate. So even though it can find valuable things, if it's not very accurate, we can't like put it on in a loop. And so there are like lifetime checkers in MSVC Visual Studio as well as in other tool chains, but there is a lot of work that needs to go in there. There is no borrow checking in any of the tools that we looked at. So that's definitely something we are interested in pursuing. And also, we debated about whether it's worthwhile to pursue a strict mode in the compiler, where obviously we don't want to restrict C++ too much. That's not our intent. But things where we say that you can and cannot do certain things, but that if you can adhere to those principles, then you do get some safety guarantees at compile time. So in places where you need to do that, you can lift the lid and still do those things, but in the safe mode, that the default would be to disallow some of these problematic patterns to be used in your code. So that's something we have also been looking at, and we are not done there, and we'll talk more about that in upcoming conferences on what we did. But this is definitely a big ticket item for our team at the moment. Switching gears, we look at a lot of interesting patterns from Microsoft, right? We work with engineers on different teams. We work with security researchers that would send us, whenever they run into interesting vulnerability patterns, they would send us those reports, and they would ask us to find those using our tools and what it would take to make it checkable at compile time. So we found different kinds of security vulnerabilities, performance problems, logical errors, and many interesting patterns that are generally fun to look at. Like we all make mistakes, but looking at it's fun to look at other people's mistakes. So security, here is an example of a security vulnerability that I wanted to share. In this case, fetch receives memory, not necessarily from a trusted source, but get memory API is supposed to fill in pname data to a piece of memory that's valid, and it should be valid up to cbmem data element bytes. And then we are trying to copy the memory that we read from in get memory into this destination buffer, which is p data. Now, as you can tell here, that what we are copying is CB data bytes from an offset of M current position. But this M current position and CB data, what is being copied, is not related to CB mem data, is not checked against CB mem data at all. So that's problematic. And we have static analysis tools that will actually flag you for this code. So it has a warning that says there's a potential read overflow using pmem data. When you are using that, the buffer is apparently unbounded by the buffer size, because the buffer size is cbmem data, and you don't have any checks for that in this code. So what the developer would do is they would go and add this piece of check in the function, and that should make it safe, right? So it says, oh, if the offset plus what you are copying is greater than cbmem data, then you return and don't try to do the copy. Apparently, that's not good enough. This is exactly the code we had. And in the field, this code actually caused a remote code execution attack. So what was happening in this case is, even though the source buffer was well checked, there wasn't a check on the destination buffer when we were trying to copy this memory. So what was happening is, because of the missing bounds check on before you call copy memory on the size of the destination buffer, we could end up copying more than it could hold, and that's really bad. So here is the mitigation that we came up with, right? So if you compare it with the previous slide here in this example, P data and CB data, they are like a pointer to a memory and its length. We have a type here called Gsl Span. It's a view, and Gsl Span is like, I'm sure many of you are familiar with the standard span type, which is now part of C++20. But before it became standard, we had it as an implementation in the Guideline support library. It's basically a pointer and its length, and it's a view over a contiguous piece of memory. So anything that's contiguous, you could create a span and share that across. And the nice thing about this span is, because we knew the pointer and the length, if you're trying to access that through the span and it's out of bounds, we can terminate the program. So even if you're not doing any checks in the program would be terminated for an incorrect access. And that's very compelling for security researchers, because when you terminate your program, it essentially transforms your security attack vector from a remote code execution to a denial of service, which is a lot more desirable. So here, as you can see, we made this a span, and the mem data, which is our source buffer from which we'll copy, that is also a span. Before I jump onto this highlight, I wanted to show that we still have this check, which is great. And when we are creating this subspan, it says, from offset, I'm going to read CB data. And when you create the subspan, if you find that you're trying to access too much, then we can also terminate your program. And then you are also copying that to a destination buffer data, which is a span. So if we know its length, and if the length is not big enough to hold, then we will again terminate your program. But GSL copy itself, has a safety check in it. So this program is like as safe as it can be. And with this change, both data and mem data are protected here. And so you get a denial of service instead of a remote code execution, which is what a desirable outcome in this case was for us. The next example is not as fun as the previous one, but it still makes an important point. Like, this was a code in one of the projects that we looked at. Common class table was a pretty expensive structure, and you would find that it's a pretty innocent looking for loop that iterates over that. It's using the range for, which is great, but except that it's not writing to item at all. This is not immutating. And there is a pretty expensive copy operation happening here. And so these are cases where we can use static analysis and improve the code by encouraging to mark these things as a const auto and the reference. So these are some of the things that we are using to improve the code that we ship externally. I wanted to talk about where we are today with Microsoft static analysis. These tools have been in Microsoft for many years now, and they're used to validate millions of lines of code. There's security development lifecycle rules that run on every piece of shipping software. It's part of the security compliance before you ship something. Every check that you saw today, there are many more that are available in Visual Studio. It's free in the community edition. The tools are run in the IDE in the background. So the idea is, as you are writing your code and saving your projects, code analysis would run in the background, and it would show you some of these warnings as green squiggles or red squiggles, depending on the severity. And that way you don't have to take an action. You would just see them just like you see errors and suggestions from IntelliSense. So we have, as of this month, I think we have more than 1 million users that have been using these analysis rules in the background. If you are not like a fan of the IDE, you can also take advantage of these rules in your build system. We have a pretty detailed blog on how you can integrate these checks in the build system, and you can also reach out to me, and I can. In fact, we have helped some enterprise customers run these rules in their build pipeline. The idea is to kind of integrate it tightly with the inner loop of developers so that it can add value before a bug is introduced. So in terms of what we saw today, there are two kinds of checks. One are simple checks, which are built upon this abstract syntax tree, or what we call an AST. We get these ASTs from the C++ compiler frontend, and then we have a plugin model that we can use to write checks. Basically, these plugins consume the ASTs from the compiler, and they can build different kinds of syntax checks on top of them. They're great for simple rules, but they're not good enough for a lot of the checks that we do. Having a framework is required for doing data flow and path-sensitive analysis. So we do have a representation where we take these ASTs and we convert them into data structure that we call control flow graphs. And the CFG layer sits on top of the ASTs. It has its own internal representation, and it has a lot of libraries, like it has its alias analysis that can say whether two different variables are aliases of each other. It also has a linear constraint solver that allows us to scale in real time, because if we have an expensive constraint solver, your analysis will take a lot more time. So we have a pretty simple linear constraint solver that really works well for most of our needs. And some of these basic building blocks have been in use for the past 10 years. So the platform is kind of pretty mature and allows us to move fast when we want to try out a new rule. In terms of what's next for us, we definitely want to invest heavily on more code safety checkers. That's one of our key differentiators and themes. I think, and this is not just our tool chain. I think I'm happy to work with the community here, and I would like to see more safety checkers available to developers, no matter what tool chain they are using. We can definitely do more here on providing bounds, types, and lifetime safety. Another important aspect for us is, as the language evolves, there are new ways people can make mistakes, and so the tooling needs of the community has to be constantly, rejuvenated. So one of the good examples there is when we had the span type as a guideline support library type, and then it became standard. Yes, we have these runtime checks, but should we just defer everything to a runtime check? I guess that's a big no for me, because if we have a static analysis tools that can actually, from a span, whether using a Gsl span or a standard span, can find these buffer overrun defects at compile time, it's a lot more compelling than a denial of service attack that you would see in the field. So definitely we would want to embrace this new types in our tools as they become part of programs. Coroutines is another good example where we've seen lifetime issues with coroutines, especially when you're using a combination of coroutines and lambdas, and you suspend something, and by the time it comes back, it's resumed. A local might have gone out of scope. So there are new ways you can make mistakes when you're using new language features, and we have to constantly keep that in mind and have rules available by default, where even though you're using these new features, we don't want you to use them incorrectly or make mistakes. So that's definitely a big investment for us. For those of you that don't know, Microsoft GSL is an open source library that my team maintains, and it has so a lot of the implementations for things like byte or span, they were part of the guideline support library before they became part of the standard. So we definitely encourage usages of Microsoft GSL within Microsoft, especially in security sensitive code bases, things like Hyper-V, where if you use a standard span and you still write out of bounds, the standard says doesn't say what the behavior should be. It's implementation defined, but GSL actually would terminate your program. So if you really want that level of safety, then you still would want to use this type. Similarly, we have narrow cast, where if you want to protect your code against data loss, and if you use a narrow cast, you would actually get an exception thrown when a data loss is happening. and you can catch these kinds of errors. So that's definitely something we want to invest in going forward as well. So I think a combination of the C++ standard, the GSL library, and core guidelines, I think that's where we want to build a community around that. Another important area for us is diagnostics. I think it's imperative that for any static analysis tools to be effective, our customers, essentially all developers, should be able to understand what's going on. There are data flow rules that detect buffer overflows for us, and some of those warnings are pretty difficult to reason about. If we can make it easy for developers to reason about what's going on, then I feel like we can have a lot better chance of people paying attention to these warnings. Similarly, we want to warn where it's most relevant. So paying attention to the source locations is very important. Like, are you warning at the right line or in the right context? So improved source locations is something that we are looking at. Path highlights, and we have a feature called key events, but it only works for a very small set of rules we have, where we highlight the path, and at every point where we take a branch, we kind of spit out what the tool is thinking on in that. And we don't have that for many of the path sensitive data flow rules, and that's another useful feature that can I think have a very positive experience for the developers. And lastly, I feel like we should be able to show defects in the code that you care about most. So while it's great you want to see warnings from headers and other external includes at some point, those are not always actionable. So we have internally used in environment variable hacks, and so in the IDE, you only see warnings from your projects. But we want to make this a standard compiler feature that works not just across code analysis, but also compiler warnings. So that way, if you care about warnings in your code, you should just be able to see that. And definitely, this is something we are going to talk about in our upcoming blogs for some of these diagnostic improvements. We also want tighter integration with developer workflows. We feel like you have a lot better chance of static analysis warnings getting the right attention when you are in the inner loop, because that's when the developers are working on that code. So we have integrations pretty tightly with the VS design time experience, where you see many of these rules kick in the background as you're writing your code. We're also working with the Compiler Explorer to make these rules. If you want to play around with snippets and see what kind of analysis artifacts would show up, we'll also have that available there. We are also working with GitHub to see if we can make this part of the outer loop in GitHub. So we'll see if we can get these rules in the GitHub security experience. One of the other things that we are looking at is we are investigating opening up this code analysis architecture to third-party plugins. Our existing ASTs that we use, they are kind of 10+ years, and while it's great in allowing us to write these rules, there are some heroic efforts needed to maintain these ASTs. There are lots of abstractions that are not available to us, and when we do these conversions from internal compiler trees to the ASTs, we have to create these hacks so that we get analysis information that we need. So we are trying to take a fresh look at if we can build modern ASTs from grounds up and make that available to the community. And using that AST, the hope is that you would be able to write meaningful semantic checks. And also at some point, we would definitely, once we have these modern AST APIs available, we would want to also make the next layer of analysis for us, which is our control flow graph layer with all these constraint solver and alias analysis available, so that it's not just us writing the checks, but we have more people that can write checks and cater to their own needs. So if you want to see more investments in this area, feel free to drop me a line. I think it definitely helps move priorities around internally based on the feedback we receive. So I'm very interested to hear if you really like to play around with this platform. If you can share that feedback, it'll help me prioritize that. So looking forward to that feedback. And yes, I would urge all of you to join into the fun, like give feedback, suggestions. Visual C++ has a pretty active presence in most social channels, including Twitter. We have a developer advocate, and they are pretty active there. You can contribute by having ideas on checks or submitting bug reports, or if you want to see any fixes for some of the rules that we have already, or even if you would like to contribute by giving us tests that you would like to see or check on, we welcome all kinds of contributions. And there are a bunch of resources, and you can go read more about the work that my team does. Most of our announcements are through the C++ team blog, and we have an exciting lineup that we will be talking about in the coming days. So if you are interested in learning more, definitely stay tuned for our announcements in the C++ team blog. Our documentation page is now very easy to edit. And I know that we can do better on documentation, and I take documentation seriously. So if you don't like documentation in code, feel free to, super easy to submit a PR yourself. And if you don't want to do that, just drop me a line, because I think we need better documentation for everybody. We also have Langtidy integration in Visual Studio. I think Langtidy is great. It has a lot of syntactic checks as you're writing your code. And so we have now two sorts of different kinds of linter checks. One is Langtidy, one is the C++ linter, which is built on our IntelliSense trees. So definitely give that a try. And obviously, if you want more semantic checks or data flow checks, then I would encourage you to use our code analysis tools. You don't have to do anything. It just kicks in the background, and you just got to pay attention to the squiggles and see if they make sense for your project. We also work with the core guidelines. So if you like to see something added to the core guidelines, or if you have comments or feedback on any of the existing guidelines that could be better, you can definitely make changes there. In fact, very recently, I was working with one of the customers that wanted a guideline added for usage of lambdas in coroutines because it was so error prone, and that issue did get accepted. So if you want to see a change, try and be part of that. You can definitely make these changes happen. If you want to try out our guideline support library, we have a GitHub repo. We try and respond to every issue within 72 hours. So feel free to interact with us on the GitHub project, and that's a pretty useful way to use types that are not in the language yet, but they're like a type extension that can help you write safe code. So definitely check it out. And lastly, I wanted to also give you a pointer to the Serif. It's like an open source static analysis log format, and every static analysis tool vendor is embracing this. So it's something that you look at other companies like Coverity or CodeQL, all of them generate Serif log formats. And most of the experience that we have currently on Visual Studio is also driven by these Serif log formats. Again, if you would like to see changes in the log format or something that you want like your feedback to be heard, there is a GitHub repo there. You can interact with us on this GitHub repo. And lastly, I would like to acknowledge our contributors that have been working in this area. We work closely with the core guideline editors, but also, these are the bunch of people that make these tools possible. So they are kind of passionate about using static analysis and have been like, and maybe some of these names are also known in other communities, but yes, they all make these rules possible. So I would like to thank them all. With that, I'm ready for any questions that you have.
Yeah, a question. Is static analysis installed separately in Visual Studio installer?
No, actually, if you install the C++ tools, it is available by default. And it's also available in the community edition. I think that's for those of you that tried it like maybe 7-8 years back, that was not the case. It was an enterprise only feature, but we made sure it's available in the community edition as well. So even students should be able to access it for free.
Can you demonstrate how to enable or disable it in Visual Studio?
I can do that easily. So essentially, you don't have to do anything here. So imagine you open Visual Studio and you start typing here. So if I, for example, remove this and then I save my file, you will get these rules running in the background, and so you would basically see the errors here. You can also run it by analyze and code cleanup, run code analysis on this project, and you can also run it by this tools menu. If you want to disable all the rules, then what you could do here is you could go here to the properties. In properties, there is a code analysis tab, and here is where we have the Clang tidy integration. For the MSVC checks that I showed you today, they are in the Microsoft tab. So once you go there, I created a custom rule set here. So by default, what you see is the native Microsoft native recommended rules. So if you don't like some of the warnings, you can create a custom rule set and create. I can show you how to do that. Or you could say that I want the minimum rules, and you can go to minimum rules here. And you could also create a rule set that says I don't want to run I don't want to see any warnings. So you can create an empty rule set, and that way you will not see any rules on your project. You can also do in-source suppressions here. So any standard pragma suppressions would work. So you can do actually for this one, we have a GSL sub. There are many ways of suppressing. So one is called GSL suppress, and then you can have 26486. So and then you can have 489.
And you probably need to save it.
Yeah, I'm going to use a different syntax. I don't know why that didn't work. I'll just use.
You probably need to save it.
Oh, I think I did. No. Oh, that's a different warning. Okay. So maybe 26. Do it again.
Comma?
Yeah, looks like that's a bug. It should work, but anyway, if you're not, if you want to use the standard pragma warning, that should work as well. So you can do a pragma warning. Suppress. And that should. I'm not sure. Yeah. And 266. And that should also work. So these you can also do in-source suppressions for anything that you want to suppress locally, but you want to keep it on for your projects. You can do that. So you can also create custom rule sets in the code analysis menu. So if you go to properties, you can configure your rule sets. So you can click on configure, and it'll open your rule sets. And if you go to the native rules, you would see that I have few rules checked in here. You can select or deselect rules. If you deselect everything and save, then obviously you will not see any rules kick in during the background analysis. But you can select whatever rules are interesting here. And that way you can configure things tailored to your project. That's I think, yeah.
All right.
The other thing I wanted to show here is these are the C++ core guideline rules that I have. So for example, we have bounds rules, which implements the bounds profile. We have const rules, which implements the const correctness rules that I showed. We have lifetime rules here. So definitely that's something we want to improve on, because we've had reports of false positives. So we now have 2 rules which are fairly accurate in this, and the rest we have moved to experimental. We want to bring them back. We also have type safety rules, and these cover things on casts that I showed up. So definitely you can try them out. And if you want all C++ core guideline rules, there is one called C++ core check rules, and that will enable all the different profiles that we have. So yeah, definitely give that a try and let me know what works and what doesn't work. All right. Any other questions?
Yeah, we actually had one in the chat window.
Okay.
Is this available on VS Code?
The answer to that is no, not today. Internally, we are experimenting with it. There is a team I'm working with that have developed a plugin. It's called, we have a code name for it called the Wave extension. If you install the plugin, what it does is it installed a Serif viewer. Serif viewer is like an open viewer that you can install as an extension in VS as well as VS Code. And the Wave extension installs that Serif viewer, runs analysis in the background, and overlays its defects through the Serif viewer. That's an internal only experience, but the VS Code team is pretty close to where I work. So I'm definitely going to be in conversations to see if they can make this part of VS Code. I think there is definitely a balance to be struck there, but we don't want to make VS Code heavy. But at the same time, I feel like if we can choose a rule set where the rules are fast enough, we can definitely have this experience in VS Code. So that conversation is happening now. But today, if you want something that's not available externally. Right. Are there any more questions?
Another question about Rust. You mentioned that in Rust there is no fall through at all supported. At least that's what the expression that I got.
Yeah, I think at the time we looked, which is last winter, that was my impression that there wasn't any fall through in the Rust language. Yes.
So if multiple branches of switch case statement or analog of that in Rust, if they are repeating, then the code will need to be repeated in multiple branches of the switch case statement.
That would be my understanding. That is correct, and which is why I think what you're describing is a very key observation. When we started looking into it, I feel like there are lots of flexibilities in C++ that we should embrace, and we should not try to take those away. So this is one thing that struck me as, yes, this is to me, this is like taking away from the, it's a bad take back from my point of view. So I think the idea is we should not want to make C++ Rust, and that's not my goal at all. But we should try and enforce these in C++ so that developers don't make these mistakes.
Yeah. Hey, Robin, I'll jump in on that one real quick. The match statement has it's a multiple select. So I just threw a link to that in the chat window.
Okay.
So that's how you would do it in Rust. You'd have a multi or an ORed condition in your match pattern.
I see. All right, nice.
Oh, sorry, I'm not able to see the chat window. Let me stop sharing my screen. Maybe that way I can see the chat window a little better.
Yes, and you can reshare the whole screen in order for this chat window to get into the recorded video, such that the video viewers can also see the link.
That'd be cool.
Okay.
Yeah, this is very interesting because I'm working in both C++ and Rust these days, so among other languages.
Oh, nice. Lucky you are.
We have a very small Rust team that's just trying to experiment. So I'm also very interested in what it does.
Yeah, we're using it fairly regularly, and there's some interesting trade-offs between the two. Let's put it that way. There's pluses and minuses like everything else.
Okay, I can see the chat window a little better now. All right. Any more questions? Hey, Robin, you're muted.
I can try to share my screen to show it in the video. So as I understand, do you see my video?
Yep.
My screen share?
Yep, we can see it.
Lloyd, as I understand, here's the multiple choice.
That's what I'm referring to. Yeah.
Yeah, I think that. Yeah.
The other one, you could go down to the one below it too. There's a 13 ...
That's a range, right?
I think that's a range. I think that,
Yes.
And what does
that
this?
is a range. Yeah, so that's a range, and it includes 19. So if you say 13 ... and don't have the equal sign,
that's 18.
It's an open range at the right. Yeah.
Right. Yeah. Equals is like including 19, and yeah, if you don't have that, it's one less than 19.
Yep.
Yeah. And we don't have to specify explicit break here anywhere, right?
No, you only get one statement. And so if you want more than one statement, you introduce a block with curly braces.
I see. All right.
So it's essentially the break statement's that comma at the end of the line.
Okay, thanks.
Using fall throughs on C and C++ switches is very common for us. However, it is actually very dangerous because there's a lot of bugs out there of accidental fall throughs, and multiple other languages disallow that because it is so dangerous of the accidental fall throughs. Either the language will have an automatic break, or I believe in C#, at the end of one switch, you can do a go to the label you want to fall through to. So that way you could actually have 4 or 5 different switch statements that all fall through to a very specific switch statement, which would be kind of handy if you have a default behavior, but you have all kinds of special case overriding that you don't want to be fall through, fall through, fall through. Because then you do fall through case if this, case if not, all that type of ugliness strewn throughout. And unfortunately, you can actually go to a label in a switch statement from outside of a switch statement. You really should never do that, but it's a real label that you can. So switches are haphazard legacy from the early days of C code. They really haven't been improved much.
Yeah, it's interesting because before C++ 17, at least in Microsoft, I had seen this Deckel spec that was invented. It was called Deckel spec fall through. And for those of you that are familiar with Deckel spec, these are strings that you can attach to symbols. So we had our own Deckel spec fall through before it became a standard attribute in the language. But there's definitely been like usages of fall throughs and seen coding conventions that encourage you to make that intent explicit. But I think I agree with you that the intent is questionable in a lot of cases. But at least gives static analysis tools a chance to kind of just be silent about it, or like other two trade-offs would be to be completely silent about it or warn all the time. And this kind of is a middle ground where, yeah, you're making your intent explicit, but yes, that doesn't mean it is correct all the time. Hey, Robin, you're muted again.
Sorry. Another interesting topic about switch case statements is the DOFS device. I'm not sure if you are familiar with that, and I'm curious what the static analyzer tool will say about that. Let me share my screen to show it. So the DOFS device is a standard C that has a switch case statement, and inside of it there is a do while statement through it, and it's a standard C. And I'm curious what your static analyzer says about that.
I'm not sure I have seen that pattern before, so I would just throw that at my static analysis engine in Visual Studio, and I can see what it does. Yeah, I'm not sure we we look for this pattern at all. So maybe we'll be silent about this.
So the article is named Duff's device.
Okay, I can definitely look at that and get back to you on what we do with this pattern. But I don't think we added anything consciously.
That's just curiosity.
I think that comes under the heading of "Don't do that."
Yeah, go ahead, Rod.
The article provides rationale for a specific case when it is very efficient, but I don't say whether it's good or bad.
I think this reminded me of another pattern. I think we just talked about go-tos in a switch, but I generally felt like in Microsoft, a lot of the especially legacy code bases, it's a very common pattern to have go-tos used for cleanups. So you would have lots of if blocks checking for error conditions, and then they would say go to cleanup, and go to cleanup, and then you have a label, and then you do cleanup. Except that in one place you would forget to do the right thing, and then you are not going to execute that cleanup code, and that will cause like file handles or some other resources leaking. And one of the things that we wanted to do is avoid that kind of a coding construct, but we didn't have anything we found in the language that we could suggest. So we created this type extension called finally. We have that implemented in the GSL library where you could do a GSL finally and assign it to like a local object. It's like an RAII object that when at the end of the block gets cleaned up, and you don't have to worry. You just do that at the very beginning and you forget about it, and then you don't have to worry about cleanup anymore. But obviously it's C++ code, so it doesn't help any C code that we have around. So that still suffers from that go to cleanup problem.
RAII helps a lot with that.
Yes, it does. Yeah.
There was one place I worked at that they had a way around go-tos. Every function had a do while statement, and you would return from the end of that, but after that would be your cleanup code. So if you had any errors in your function, you would do a break, and it would break out of the do while statement and hit the cleanup code at the end. It's a go-to without go-tos.
That's interesting. And
you can
other...
also put the break in macros also. So you put a macro on every line that checks the error return code, and if there was an error return code on that line, it would just do a break. Ugly, but that was the standard at that company. I don't think they're in business anymore.
Is that related?
Maybe not. You would have to worry about buying their products. So.
Yeah, I've seen coding conventions evolve out of like the tooling needs. Especially for static analysis, it makes me a little sad if you're trying to write code just to satisfy the tool without adding much value. But I've seen like we used to at some point run code coverage tools, and any code that would check for an error condition and terminate would have poor coverage numbers just because those error conditions were not common enough. So some teams had a convention where they would create these deep nested if blocks where they were always checking for the success. And that way your code coverage would be a little bit better because you don't have these if failure return, and none of those blocks would be executed. But yeah, I can't say I supported that convention back in the days. Yeah, somebody mentioned macros, but macros are something that we don't do a great job with our diagnostics, just because by the time we see macros in the ASDs today, they have already been expanded by the preprocessor. So it's kind of difficult to provide diagnostics where the macro is defined, and that's something we are again looking to improve with our ASD modernization effort.
So do you end up squiggling macros and then say, give some really weird error that the macro doesn't look like? because that's how it expanded?
No, actually, let's take an example, right? So say you have a rule that says you should convert. It's a very syntactic check that says anytime you see a null on a pointer, you should use a null pointer. And all toolchains have that rule, right? Clang has that, MSVC has that. You have these definitions, you have these asserts in this assert CRT debug headers, which are like system headers that you can't change. And these are actually coming from macros in those headers. But because these macros end up in the source files, we end up warning on these macros saying, hey, you should change this to null pointer, except that they are not defined in that source file. Those macros are defined in standard system headers. And so the diagnostic is accurate and it's understandable, but the developers are not too happy to see us pointing out an error on a macro that they just can't change. And it would have been nicer if we could provide that error where the macro was defined, which would be in the header itself, in the system header itself. And that way, the standard suppressions that if you're suppressing out errors on system headers, you wouldn't even see those. I think those are like the more typical problems. I've also seen very ugly nested macros, and we have had to fix bugs because if you have a lot of nested macros on a single line, we had bugs where the suppression mechanism, which creates warning states and all of that, didn't work around macros. So that is fixed now. But I think it's more about warning at the right level. That's a problem. Right. Any more questions?
Okay, well, if that wraps it up, we can go ahead and stop the video. If people want to hang out and chat, please feel free to. Essentially the virtual meeting stays open until the last person leaves. So feel free to hang out. And thank you, everyone, and thank you, Sonny. It was a great talk.
Yeah. Thank you very much. Yeah, this was a nice audience to interact with. I would definitely stay tuned for future talks. And if my team is interested in the lightning talks, I'll let you know.
Yeah, and basically let me know because I'm always looking for speakers. So I've got most of this year booked, but very soon I'll be starting to think about January 2022. So
sounds great.
Okay, I'll stop recording then. See you.